Hi everyone, in this video I will be discussing about complex numbers. So for instance, if we have the square root of -9, so take note that we won't get a real number out of a square root of a negative number. The square root of -9 is not a real number since there is no real number that we can square and get -9. But we have a rule, if you can still recall, we have a rule for radicals that if a and b are both positive, then the square root of ab is equal to the product of the square root of a and the square root of b. So for a second, let's try to forget the restriction that a and b should be negative. Let's try to apply the certain rule to this given example. So if that's the case, the square root of -9, we can write that one as the square root of 9 times -1, right? And if we simplify, 9 is a perfect square, so we can get the square root of 9, which is 3. We can put that outside of the radical symbol and we are left with -1. How about if we have the square root of -100? So still the same thing, we can simplify that one as the product of 100 times -1, right? And 100 is a perfect square, so we can extract the square root, which is 10, and again we are left with -1. Lastly, if we have the square root of -5, let's say -5, so we can express that one in the form 5 times -1. Now since 5 is not a perfect square, so we can simply rewrite that one as the square root of 5 times the square root of -1. So if you try to observe the three given examples, it is common among the three that we have square root of -1 there, also here, and also here. So what is this square root of -1 exactly? So by definition, in mathematics, we have a certain number denoted by I, and I is equal to -1. And if we try to square both sides, so squaring both sides of the equation, we would get I squared is equal to -1. So in some way, I is the only number that we can square and get a negative value. So going back, if we have the square root of -9, we can write that as 3i. Why? Because if we apply the rule earlier, we can write this one as square root of 9 times -1. Square root of 9 is 3, and square root of -1 is I. So if we also have the square root of -100, we can rewrite, or we can simplify that as 10i. And if we have the square root of -5, we can simplify that one as square root of 5i. So 5 will still be in the radical symbol since this is not a perfect square. we cannot find a certain number that we can square to get exactly 5. Okay. So going back to our main topic, complex numbers. So complex numbers are numbers in the form a plus bi. So this is the standard form of complex numbers. Take note, a and b are real numbers, and they can be anything. A and b can be positive, it can be negative, it can be zero, it can be integers, it can be fractions, it can be decimals. It actually doesn't matter. A is called the real part, and b or bi, that is our imaginary part. Imaginary. Let me give some examples. We can have 3 plus 5i. So that's an example of a complex number. We can also have, let's say, the square root of 6 minus 10i. That's a complex number. We can also have, let's say, 4/5 plus I. We can also have actually 16i. And we can also have a certain number, let's say 130. So these are all examples of complex numbers. By the way, for your attendance, kindly comment down in the comment section your full name, your course, your block number, and for your participation, kindly comment also an example of an imaginary, or of a complex number. So going back to the examples, let me just try to focus or explain the last two examples, because the first three are clear and evident that these are really complex numbers. How about for the last two examples? 16i is a complex number. Also, 113 is also a complex number. Why? I mentioned earlier that a and b can be 0. So if in the case that a is 0, we would only be left with 16i. So this number can be called as a this is a purely imaginary number, because the real part is 0. So that's purely imaginary. Now how about 113? So if in the case b will be 0, so we are only left with the real part. Okay? So we can say that real numbers are a subset of complex numbers. Next, let's talk about the conjugate of complex numbers. So what are conjugates? Let me show you an example. If we have a plus bi, the conjugate of that is a minus bi. So it's actually the same or the opposite of the complex number. So it's the same real part, it's the same imaginary part. The only difference is that the sign. So if the imaginary part here is positive, the conjugate should be negative. If the imaginary part is negative, the conjugate should be positive. Let me show you some other examples. So let's say we have 3 plus 1/2 I. What do you think is the conjugate? So the conjugate of that complex number is 3 minus 1/2 I. Next, if we have 12 minus 5i, the conjugate of that complex number is 12 plus 5i. So again, just simply reverse or look for the opposite sign. Next, if we have 1 minus I, so the conjugate is simply, of course, 1 plus I. How about if we have 45i? So here, the real part is 0. We are only left with the imaginary part. So, for its conjugate, it's simply 45i. Why? Because let's say we have 0 as our real part. We have 0 there. So, if we remove 0, it will look like this. Okay? Next, how about if we have simply the number 101? What do you think is its conjugate? So if you thought of 101, that's actually correct. So the conjugate of a real number is simply the number itself. Why? Because in this case, the imaginary part is 0. So let's say we have plus 0i, we have minus 0i. So even if it's positive, even if it's negative, it will still be 0. Okay? So that's for conjugates. Now let's talk about addition and subtraction of complex numbers. So if we talk about addition and subtraction, we can compare this one to addition and subtraction of polynomials. Let me give an example. Let's say we have negative 4 plus 7i plus, that's the quantity of negative 4 plus 7i plus the quantity of 5 minus 10i. So just like polynomials, we can add or we can subtract terms that are similar. So in complex numbers, we can add the real parts, add or subtract. We can also add or subtract the imaginary part, but never do not add the real and the imaginary. That's a big no-no. Okay? So if we simplify that one, if we remove the parentheses, we will have negative 4 plus 7i plus 5 minus 10i. So simplifying, that's negative 4 plus 5, of course that's 1. 7i minus 10i, that is simply negative 3i. For your final answer, always write it in standard form, a plus bi or a minus bi. Second example, let's say we have 4 plus 12i, quantity of 4 plus 12i minus the quantity of 3 minus 5i. So if we simplify, we remove the parentheses, that's 4 plus 12i. Since this is negative, 3 will become negative, 5i will become positive. Then simplifying, 4 minus 3, that's negative 1. 12i plus 5i, that is 17i. So that's in standard form. That's already simplified. That's our final answer. Number 3, suppose we have 5i minus quantity of negative 9 plus I. So if we remove the parenthesis for the second quantity, that's 5i, negative negative, that will be positive 9. Then we have negative I. So simplifying, that will give us 9. Then 5i minus I is simply 4i. Alright? If you have questions, clarifications, feel free to comment your questions down below in the comment section so that I will be able to answer and entertain your queries. Next, let's have multiplication of complex numbers. So same with addition and subtraction, think of it as simply multiplying polynomials. Example number 1, we have 7i times the quantity of negative 5 times 2i. So, distributive method, distribute 7i to both terms inside the quantity. That's 7i times negative 5. That will give us negative 35i. Then 7i times 2i, that is 14i squared. Now, if you can recall earlier, I squared is equal to what certain number? I squared is equal to negative, or I squared is equal to negative 1. So negative 35i plus 14 times, that's negative 1. So writing the final answer in standard form, that's negative 14 minus 35i. Okay. Number 2, we have 1 minus 5i times the quantity of 9 plus 2i. So in this case, since both quantities are composed of binomials, we can apply the FOIL method. So first, that's negative 9, outer, that's 2i, inner, that's positive 45, that's positive 45i squared. I'm sorry, first outer, that's only positive 45i. Then last, that is negative 10i squared. So simplifying, so that's negative 9. We can combine the middle terms since they are similar. So that will give us 47i. And I squared again, that's equal to negative 1. So if we simplify, that will become now positive 10. And 10 minus 9, that's 1 plus 47i. For example number 3, we have 1 minus 8i times a quantity of 1 plus 8i. If you would recall, for special products in polynomials, we actually have the rule for the product, the sum and difference of two squares. So we can try to apply that here. Let's try. So square of the first term, that's simply 1. Then square of the second term, but the sign is negative, so that will give us 64i squared. So if we apply the FOIL method, we also will have, that's 1 outer, that's positive 8i, inner, that's negative 8i, last, that is 64i squared. It's still the same actually with this one, since 8i minus 8i will be 0. Okay, so let's just erase this part. And again, since I squared is equal to negative 1, we can further simplify. It's negative 1, so that will become now positive 64. Our final answer is 65. Now, in general, if we have the product of conjugates in polynomials, it's the product of the sum and difference of two terms, but here for complex numbers it's the product of conjugates. So again, if we use the FOIL method, that's a squared. Outer will give us ABI. Inner will give us positive ABI. And last, that will give us positive BI squared, or B squared. I'm sorry. Wait, there's no more space. So again, that's A squared, outer, ABI, inner, positive ABI. Then for the last, that's negative B squared, I squared. So this one will become 0. We will be left with A squared minus B squared, I squared. But then again, since I squared is equal to negative 1, and negative times negative will be positive. So therefore, generally, for complex numbers, the product of conjugates is equal to the square of the first term, the square of the second term, and the sign is positive. So that's A squared plus B squared. For the next part, let's talk about rationalizing complex numbers. So if we rationalize, we try or we simplify the given complex number in order to rewrite it in standard form. So let's have an example. Let's say we have 3 minus I divided by or over 2 plus 7I. So this would seem as division of complex numbers, but what we actually do is simplifying the complex number. Now, as a rule, we cannot have imaginary numbers for our denominator if we would like to simplify complex numbers. So what we need to do is we can simplify by multiplying the conjugate of the denominator to both the numerator and the denominator. So it will look like this. So the conjugate of 2 plus 7i is of course 2 minus 7i, right? Over 2 minus 7i. Okay? So if we simplify that one, we use the FOIL method. For our numerator, that will be, that's 6. Then outer, that is negative 21i. Inner, that's negative 2i. Then last, that is positive 7i squared. Now for our denominator, I told you earlier that the product of conjugates is equal to A squared plus B squared. So simply square the first term. Of course, that's 4. Square the second term. That is 49. And the sign is positive. Okay? So simplifying, that's 6. That is equal to negative 23i. And since I squared is negative 1, that will become negative 7 over 4 plus 49, that's equal to 53. And further simplifying, 6 minus 7, that's negative 1 minus 23i over 53. For complex numbers, we can rewrite this one in the form A plus or minus BI. So, for our final answer, we have negative 1 over 53 minus 23i over 53. So this is A, this is our real part, this is B, this is our imaginary part. And as I've told you in the first part of our video, A and B can be fractions. For our second example, we have 3 over 3 over 9 minus I. So if we would rationalize, the very first thing is to multiply the numerator and the denominator by the conjugate of the denominator, and the conjugate is 9 plus I over 9 plus I. So multiplying the numerator and the numerator, that's 27 plus 3I. And again, rule for the product of conjugates, to simply square first term. That's 81, because 9 squared is 81, plus I squared. And I squared, if we simplify, it's 27 plus 3I. That's 81 minus 1, correct? It's 81 minus 1 squared. No, I'm sorry. It should be 81 plus 1 squared. And actually 1 squared is simply 1, right? So that's simply 1. And 81 plus 1, that's 82. So we have 27 plus 3I over 82. So if we further simplify, that's 27 over 82 plus 3I over 80. So this is our real part. This is the imaginary part. So let me just clarify the conjugate, the product of the denominators. So for that, we have 9 minus I times 9 plus I. So if we use FOL method, that's 81. That's 81. Then outer, that's 9I. Inner, that's negative 9I. Of course, that's 0. So minus I squared, right? So 81 minus I squared, as we know, is negative 1. So that will be 81 plus 1. So that should be 81 minus, should be 81 plus 1. So still following the rule, that's the square of the first term, square of the second term, then the sign is positive. For our third example, example number 3, let's have 8I over 1 plus 2I. Still the same thing, multiply both numerator and denominator by the conjugate of the denominator, which is 1 minus 2I over 1 minus 2I. So multiplying, we will have 8I minus 16I squared over square of the first term, that's 1, plus square of the second term, which is 4. So simplifying the numerator, that's 8I. I squared again is negative 1, so that is positive 16 over 5. And writing it in standard form, we will have 16 over 5 plus 8I over 5. By the way, for I, you can actually put it here, or you can also put it here in the numerator, whichever is correct. Lastly, let's talk about powers of I. So let's take a look at what will happen if we will raise the number I to different powers or to different exponents. So if we have I raised to 1 or simply I, we know that that's simply I, right? Or that's the square root of -1. Or square root of -1. Now, if we have I squared, we know from the previous examples that negative or I squared is equal to -1. If we have I cube, since we know, or let's try to rewrite that one as I times I squared. Now, I is simply I, and I squared is equal to -1. So that will be equal to -I. If we have I to the 4th power, we can rewrite that one as I squared times I squared, or simply raise it to another exponent 2. So we know that I squared is -1, and if you square that one, that will be equal to 1. Next, if we have I to the 5th power, we can rewrite that one as I times I to the 4th. And we have we know that I to the 4th is simply 1. So that is simply I. If we have I to the 6th power, we can rewrite that one as I squared times I to the 4th. By the way, you might be asking, rules of exponents, right? If we have the same base, we can simply add the exponents. 2 and 4, that will give us 6, okay? So going back, I squared, as we know, is -1. I to the 4th is 1. Therefore, I to the 6th is -1. What if we have I to the 7th power? So we can rewrite this one as I times I to the 6th. And we have I to the 6th is -1. Therefore, I to the 7th is -I. And if we have I to the 8th power, so we can rewrite that one as I to the 4th squared, because 4 times 2, that's 8. So we know I to the 4th is 1, and if we square 1, of course, that will give us 1. So if you try to observe, so we have I, -1, -I, 1. I, -1, -I, 1. So there is actually a certain pattern, and all powers of I can be reduced to one of the 4 possible answers, and actually they repeat every 4 power. So this is actually convenient so that it will be easier for you to remember. So that ends the discussion for complex numbers. Again, if you have questions, just comment it down on the comment section, or you can also ask your questions in our group chat so that I will be able to entertain and answer those. Thank you so much, you guys, for your time. You take care always. Bye bye for now.